Okay, we're finally getting into trig today, so we're going to talk about the trigonometric functions. There are the three that you're familiar with of sine, cosine, and tangent, but we also have reciprocals for all of these different trig functions. So we'll talk about those with cosecant, secant, and cotangent. So first off, you probably remember from geometry and algebra 2 that a trig function is the ratio of sides of all the lengths of our right triangles. Trig functions only work with right triangles, so primarily when we talk about trig, we're only dealing with right triangles, which is kind of crazy to think that we have an entire class that's just devoted to right triangles itself. When we have a ratio of sides, it depends on which angle that we're standing at. So I'm going to stand here in this corner. So we're looking at these ratio of side lengths, and this is going to be my theta. And theta is just a generic, just like an x value for algebra. Theta is our variable of choice when we represent an angle. If I'm standing there at that angle, then I can classify this side across from my angle as my opposite side. And I can classify this angle that's right next door to my, or side length that's right next door to my angle as my adjacent side. And our angle, our right angle that's in our picture, the side length that's across from my right angle is always my hypotenuse. So sine is the ratio of my opposite side to my hypotenuse. Cosine is the ratio of my adjacent side over my hypotenuse. And tangent is the ratio of my opposite side over my adjacent. You just have to be careful of where your angle is. So if I redraw this triangle, and instead of standing at that angle, if I'm standing up here at this angle, my hypotenuse doesn't change because it's still across from my right angle, but my opposite and my adjacent sides flip, because now I'm standing at this corner and I'm looking across my triangle at this side length, which is now classified as my opposite, and this side length right next door would be my adjacent. So that's just the background of using sine, cosine, and tangent. There's a mnemonic device that might help you remember. Probably remember it. SOHCAHTOA. It represents all of the different ratios that we're looking at. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So we have reciprocal identities that go along with them. So cosecant, represented by the CSC, this goes along with sine. So it's the reciprocal of our sine. So since it's the reciprocal of sine, and sine is defined as the opposite over hypotenuse, then cosecant is defined as my hypotenuse over my opposite. It's that entire thing flipped. So let's say that your sine value is 1/2. That means your cosecant value would be 2 over 1, or 2. Secant goes along with cosine, so it's the reciprocal of cosine. Since cosine is adjacent over hypotenuse, then our secant is going to be hypotenuse over adjacent. And cotangent, unsurprisingly, goes along with tangent. It's the reciprocal identity for that. Since tangent is opposite over adjacent, if we flip that around, we get adjacent over opposite. So the first couple examples, we are just looking for the cosecant or the tangent or whatever value that we're looking for, the reciprocal identity that goes along with it. So let's say that we are given that sine is the square root of 7 over 3. So this would be our opposite side and our hypotenuse, if we look at that. Since we're looking for cosecant, we would have our opposite over, our hypotenuse over our opposite. Just talking about sine there for a second. Since our hypotenuse is 3 and our opposite side is square root of 7, our cosecant would be represented that way. However, somewhere down the line, some mathematician decided that we can't leave a square root in the denominator, that it's not simplified, so we have to do this special thing called rationalization. And what we do is we take that radical in the denominator and we multiply it on top and bottom to rationalize. On the top we just put them together as 3 root 7, and on the bottom these things will cancel out. So root 7 times root 7 is is root 7 squared, and the root and the square cancel, so we just are left with 7. So that would be our answer for cosecant, given that this is the sine. Now, you don't have to necessarily do this rationalization or show this step. Like if you're already pretty confident and you know that when you flip this over you'll get this and then you'll have to rationalize, that's fine. Like once you do these things enough, you'll probably be good at it and you don't have to show me necessarily this step. Okay, they're telling us, for example, too, that the cotangent of this is still some angle, but it's an angle alpha, is negative root 5 over 2. So we're dealing with cotangent here, so this would be our adjacent side and our opposite side. And we're looking for the tangent of alpha. So we need to flip this around. So the 2 will be on top, the square root of 5 will be on bottom, and you can just put that negative out front. You could put that negative really with the 5 or the 2, so same thing here, you could put it with either or out front, you just can't do it with both. And again, we've got this square root in the denominator, so I'm going to rationalize. So on top I'll have a negative 2 root 5, and on bottom root 5 and root 5 will just give 5. So again, having the negative in front of the 2 or in front of the 5 or out front all mean the same thing. It's just that thing is negative. Number 3 is a little bit different. So we're solving for an x value given these two equations. Now we know that cosecant and sine go together, and cotangent and tangent go together, and secant and cosine go together. So we're given something that is really similar. So what we want to do is we want to manipulate this and manipulate it in some way so we can have the same trig functions on either side. So secant again is 1 over cosine. So since I have 1 over cosine over here of something, this is just my angle. I know that this is true. Secant of theta equals 1 over cosine of theta. That's what I really have. So I can replace this stuff, the 1 over cosine, with secant of my angle. So now that I have the same trig function, like these are all identical, and you're taking it of some angle, now I can set this stuff, it's like secant of stuff and secant of stuff, I can set the stuff equal to each other because that must be true. And then once I'm there I can solve, so I'll add the 2x over, I'll subtract the 5, or the 1, excuse me, and I'll get x will be negative 6 over 5. Again, the main idea is that we want to have the same trig function on both sides so that we can get to this step and have the trig function of an angle so we can set the angles equal to each other and solve. Okay, so that's the first part. Is just dealing with manipulation on sine, cosine, tangent, and the reciprocal identities. The next part is actually drawing the reference triangle in the Cartesian plane. I talked about this in my video yesterday about angles and how we generally we draw those, or it's important to draw angles in our Cartesian plane because we are looking for some reference triangle or some reference angle. We're going to do that a ton. A reference triangle is this triangle that's formed with the terminal side, and it's something that's always with the x-axis. So yesterday we talked about how this was like our initial side. So if I have a terminal side like this, then I can form a right triangle that's called a reference triangle within these different quadrants. So this would be my theta. I drew my triangle too small. This is my theta. This would be my x value that I'm looking at, how far on my x-axis. This would be my y value that I'm looking at. This point up here is the coordinate point x comma y. And this right here we're going to call r. So since I have this right triangle that's formed, that means I can use some trig values. So I can represent sine of theta and cosine of theta and tangent of theta, and once I'm there I can also find all of the corresponding reciprocal identities. So if I was standing at this angle, my sine value or my sine of that angle would be opposite over hypotenuse, so y over r. My cosine of this angle would be adjacent over hypotenuse, so x over r. And my tangent of this angle would be opposite over adjacent, which is y over x. So this right here is called my reference angle. So that's the angle that touches the x-axis. It's always touching the x-axis, and it's in the reference triangle itself. So for example, I'm going to draw a new one up here. If I have this terminal side down, I'll do it up here. If this is my terminal side, this would be the angle that is made with that, but my reference angle, once I drop down and make my triangle, this angle right here is my reference angle. It's the one that's formed between the x-axis and the terminal side. So this would be my reference angle, but this would be, you know, the 135-degree angle to form the terminal side, but this is actually the reference angle that I'm looking for in my triangle. That's important because our angles are defined in a right triangle from 0 to 90 degrees. We can't have anything, we can only have acute angles in our right triangle, so it won't make sense or wouldn't make sense to have a 200-degree angle for our sine, cosine, and tangent. We have to make this triangle that's formed and then come up with a reference angle from that. Y and x, as we're looking at, as you can kind of see here, these things are direction dependent. That means that it's possible for sine and cosine and tangent to be negative because your x and y coordinates could be negative. And if I'm in this quadrant, then this x value that I have is going to be some negative number. So this will be something that's negative. But this y value that I have is going to be something that's positive. So I can come up with depending on what quadrant you are, these things could be direction dependent. The hypotenuse, on the other hand, we're always going to consider that as positive. The hypotenuse is really the distance between the origin and that coordinate point. So distance is always positive. If we can say that the x and y coordinates are direction dependent, then that kind of eliminates then the hypotenuse from being negative as well. So we're going to do 3 examples to kind of solidify this idea of drawing reference triangles. We're going to find all the trig values, trig functions for some reference triangle plotted at some coordinate point. So it's telling us in this problem that our terminal side is through 3, 4. So I'm going to plot that. So that is the coordinate point. And if our terminal side is that, then we would form our triangle by connecting the origin with that point, and we're forming then this reference triangle in the first quadrant. So this is our x value, it's 3. This is our y value, which is 4. And then we can either use Pythagorean theorem to find our hypotenuse, or lots of you know already that this is a 3, 4, 5 triangle, so you should get 5 for your r value. So if we're coming up with now our 6 functions, we have sine, cosine, tangent, we have cosecant, secant, and cotangent. We just need an angle to figure out what these values are going to be. And that angle is always formed again with the x-axis and the terminal side. So this will be our theta. That allows us to define an opposite and adjacent side. So if I'm standing here at this angle, my opposite side is 4, my adjacent side is 3, and then my hypotenuse is 5. So sine would be 4 over 5. Cosine would be adjacent, so 3 over hypotenuse, which is 4, and tangent would be opposite over adjacent, 4 over 3. So we can come up with all these ratios. When we find our reciprocal identities, this one's kind of nice. All we have to do is flip all these over, take the reciprocal, so 4 over 5 becomes 5 over 4 for cosecant. Secant is 5 over 3 when we flip over cosine, and then tangent is 3 over 4. Okay, let's do one more. That's a little bit simple. So here's our Cartesian plane. We're again finding all of our 6 trig functions. To test yourself, because I'm pretty confident that some of you are already remembering doing some of these things in Algebra 2, or you're pretty comfortable, you can pause this video right now, try this example, and then just double check your answer. So if we're plotting this coordinate point, that's going to be down here in quadrant 3. So I'm not even going to plot that point, but I am going to draw my reference triangle. So it's somewhere down here. Again, not to scale. I drop this all the way up to the x-axis to find my reference triangle. Make sure that you're not drawing your triangle this way. It's always, again, between the x-axis and that coordinate point. This makes our angle in our triangle here. So that's our theta value. Our y-coordinate is going to be -12. Again, it's direction dependent, and since I'm in our third quadrant, both these values are negative. My x value is going to be -5 along my x-axis. And this is a 5, 12, 13 triangle, or you could use the Pythagorean theorem to solve for your r value, which should be 13. So this means since I'm in this quadrant, my sine value, since it's going to be opposite over hypotenuse, and my opposite side is -12, and my hypotenuse is something that's always positive, my sine is going to be negative in this quadrant. My cosine value, same idea. This is my adjacent side, which is negative, and my hypotenuse is positive, so this thing is going to be positive or negative. And my tangent, opposite, -12 over adjacent, -5. These negatives, a negative over negative, is going to become a positive value of 12 over 5. My cosecant, I can just flip this around, so I'll get -13 over 12, or 13 over -12, or negative fraction 13/12. It doesn't really matter. So the same thing, if I flip it around, I get -13/5, and this one should be +5/12. Okay, last one for today. This time we are looking for the, again, 6 trig functions. I'm just going to write down the first 3 right now. Through, for this angle whose terminal side is through -2, 2. So for that one, -2, 2 is going to be in quadrant 2. Here's my terminal side. When I draw my reference triangle, I want to make sure that I'm forming it with the x-axis. So here's my right angle. Here's the theta that I'm forming. My x value is going to be -2. My y value is +2. And this isn't a special triangle or one that a Pythagorean triple, so we're going to solve it with the Pythagorean theorem to come up with our hypotenuse. This is 4 plus 4 equals r squared. So 8 equals r squared. Take the square root, get the square root of 8. I'm going to rationalize that, so thinking of perfect squares that go into 8. 4 times 2 is something that would make up 8, and I can take the square root of these things individually, so I'll get 2 square root 2. So that'd be the simplified version. It's important that you do this. You should rationalize. Oh, sorry. You should rationalize, and you also should simplify your square roots. So if I'm standing at this angle, here's my hypotenuse now. My sine value is opposite over hypotenuse, so 2 over 2 root 2. Now these 2's will cancel out, so I'm really just dealing with 1 over root 2, which that's something with this radical in the denominator, so I'm going to rationalize that. On the top I get 1 times root 2, which is just root 2, and on the bottom 2 root 2 times root 2 is 2. Cosine, something similar will happen. So here's my angle. I would do adjacent, which is -2 over hypotenuse, which is 2 root 2. Again, these 2's will cancel. They'll reduce down. I'll be left with 1. So I'll have -1 over root 2. That has that radical in the denominator, so I'm going to rationalize. So I'll get -1 times root 2, which is root 2. And on the bottom, root 2 times root 2 is 2. In tangent, last but not least, our angles here, it would be opposite over adjacent, so 2 over -2. which is -1. So we did all three of those. I'm going to come up with then the other three. Now what I could do for cosecant is take the simplified version of sine and flip it around again. So this time I'd have 2 over root 2. And then 2 over root 2 would be something I need to rationalize. So I could rationalize that out. And I'd get 2 root 2 over 2. And then I'd simplify the 2's and I'd get my answer. However, that is more work than you need to do. So instead, don't do that. I would go one step further before we actually rationalize this, the 1 over root 2, and just flip that. So instead, our answer would be root 2 over 1, flipping that one. And that just allows you not have to rationalize again. It's not wrong if you go for the rationalization process again, but it would just be a longer process. So root 2 over 1 or just root 2. Secant, again, I'm going to go the step before I rationalize. So I had -1 over root 2. So if I flip that one around, I'll have still a negative. And flipping this would be root 2 over 1, so negative root 2 for my answer for secant. And cotangent, if I flip either this one or this one, -1 over 1, if I flip that around, I should still get -1. Okay.